Welcome back to The Explainer. Today, we are decoding the absolute powerhouse that is a nuclear power plant. We're literally going to trace the journey of the atom, starting way down at the microscopic level of nuclear fission and zooming all the way out to the massive landscape-altering infrastructure you need to actually sustain and capture that reaction. It's going to be a fascinating ride, so let's just dive right in.
Real quick, here's our roadmap for today. We're covering megapower and plant scale, taking a look inside the nuclear reactor, and examining the fuel, specifically U-235. After that, we'll get into moderators like D2 and carbon, the control rods, and wrap it all up with the cooling tower.
All right, starting off with Section 1, Megapower and Plant Scale. Let's establish the sheer physical footprint we're dealing with here.
So, the source data explicitly slaps the label mega on the power capacity of these facilities, and honestly, that's almost an understatement. In grid terms, we aren't just talking about a really big building. We are talking about baseload power generation, cranking out thousands of megawatts or gigawatts of continuous electrical energy. This mind-boggling scale fundamentally dictates literally every single engineering decision made at the facility. Because generating power at a mega capacity means you're managing extreme thermal outputs and you need high-voltage transmission lines that can seamlessly feed into national grids without even a hiccup. It is an absolutely massive kinetic and thermal balancing act.
And to support that kind of baseload output, well, you need an immense spatial footprint, which is anchored by a strict 5-kilometer exclusion and safety area. Think about that, 5 kilometers. Securing a radius that large involves some pretty intense logistical and regulatory hurdles. I mean, this isn't just empty land we're talking about. It's heavily monitored zoning designed specifically for emergency planning, environmental mitigation, and tight security control. Long before a single drop of concrete is poured, engineers and urban planners have to obsess over local hydrology, seismic stability, atmospheric dispersion, the whole shebang. The sheer geography required means these mega facilities practically recenter the entire landscape they sit on.
Moving right along to Section 2, inside the nuclear reactor. This is the central hub.
The reactor itself is without a doubt an unparalleled feat of material science. This core structure doesn't just house the atomic reaction, it is engineered to withstand internal environments that are frankly hard to even imagine. We're talking about heavy steel pressure vessels, often several inches thick, operating under immense atmospheric pressure just to keep cooling water in a liquid state, even when it's pushed way beyond its normal boiling point. And the containment architecture surrounding that core, it's usually this heavy-duty combo of massive steel liners and incredibly dense reinforced concrete. All of that is strictly designed to make absolutely sure the intense radiation and pressure variables of the fission process stay completely locked away from that outside 5-kilometer zone. Okay, zooming in for Section 3, the fuel, U-235. This is where we get into the microscopic power. So, uranium-235 acts as the primary fuel here for one very specific thermodynamic reason. It is fissile. Unlike other heavy isotopes out there, U-235 has this unique atomic structure that allows it to easily absorb a free, low-energy thermal neutron. And when it catches that neutron, the nucleus becomes super unstable and basically instantly splits into two lighter fission products. That split releases a tremendous amount of kinetic energy, which we ultimately harvest as heat, by the way, along with 2 or 3 extra free neutrons. Those newly freed neutrons then go right on to split other U-235 atoms, and boom, you've got the continuous, self-sustaining chain reaction you need to generate megascale power. It's literally a microscopic domino effect.
Now, our source data also draws a really distinct comparison between U-235 and the isotope 232, specifically thorium-232. And this is a crucial technical distinction to grasp. While U-235 is fissile and can just directly sustain a chain reaction on its own, thorium-232 is what we call a fertile material. It can't just split on its own by absorbing a low-energy neutron. Instead, when thorium-232 absorbs a neutron inside the reactor, it undergoes a series of beta decays and actually transmutes into uranium-233, which is fissile. So understanding the precise difference between a direct primary fuel like 235 and a fertile breeding alternative like 232, well, that's absolutely central to modern reactor design and optimizing fuel cycles over the entire lifespan of a plant.
Let's jump to Section 4, moderators, specifically D2 and carbon. This is all about balancing the reaction. To actually sustain that fission of U-235 we just talked about, those newly released superfast neutrons have to be slowed down to become thermal neutrons, and that is exactly where heavy water, or D2O, and carbon come into play. See, if a neutron is moving too fast, it's just going to bounce right off the uranium nuclei without triggering a split. No split, no power. But by surrounding the fuel with heavy water or reactor-grade carbon graphite, those fast-moving neutrons collide with the deuterium or carbon atoms. These little collisions bleed off the kinetic energy without the neutrons actually being absorbed by the moderator material itself. It effectively downshifts the neutrons to the perfect thermal speed required to penetrate the next U-235 nucleus. It's an elegant way to keep that continuous chain reaction perfectly, beautifully balanced.
All right, Section 5, the control rods. Let's look at the safety mechanisms.
So while moderators slow neutrons down so the reaction keeps going, control mechanisms do the opposite. They're designed to absorb neutrons entirely, to throttle, or even completely halt the reaction. Your standard control rods are built from elements that have massive neutron absorption cross-sections, things like silver, indium, cadmium, or boron. Now, our source material also specifically references this term bonhomie. In the context of localized operational terminology from the data, that actually refers to a specific boron-based mitigation matrix. Basically, it's a specialized chemical slurry injected right into the core environment to act as a liquid neutron poison. Both those rigid control rods and this specific boron liquid system work in tandem to guarantee fail-safe neutron absorption.
The operational mechanics of these elements are just incredibly responsive. Step 1 is inserting these neutron-absorbing materials deep into the reactor core, which fundamentally changes the atomic math. The rods capture those free neutrons before they ever even get a chance to collide with the uranium-235. Step 2 is simply controlling the power based on that. The deeper those rods go in, the more neutrons get stripped out of the equation, slowing the rate of fission and bringing down the thermal output. Think of them as the brakes for our giant nuclear engine. It's a real-time thermodynamic throttle. And in an emergency scenario, these rods can be dropped entirely into the core in literally a fraction of a second, absorbing all the neutron flux and instantly shutting down the whole atomic chain reaction.
Finally, we've arrived at Section 6, the cooling tower, the iconic external structure.
So the massive thermal energy generated by all that fission is used to boil water, create steam, and spin the turbines that actually generate our electricity. But once that steam passes through the turbines, it has to be condensed back into liquid water so it can be reused. That thermodynamic process requires some massive heat exchange, and that is handled by the iconic hyperbolic cooling tower. That sweeping, inward curving shape you always see, it's not just for looks. It's specifically engineered to create a natural draft by leveraging the Venturi effect. Hot water from the condenser gets sprayed into the lower sections, and as some of it evaporates, it absorbs a huge amount of latent heat. That hyperbolic shape accelerates the rising hot air upward and out, which in turn pulls cool ambient air in from the bottom. It creates this highly efficient, entirely passive cooling cycle. Just brilliant engineering.
As we wrap this explainer up, I really want you to consider the profound engineering paradox we've just unpacked here. We are extracting gigawatt-scale, landscape-altering power, all by manipulating the fundamental instability of an invisible, microscopic isotope. Looking ahead, the question isn't just how a single atom of uranium-235 connects to a giant cooling tower in a 5-kilometer surrounding area to generate megapower. The real question is, as global baseload energy demands absolutely skyrocket, have we reached the peak thermal and geographical efficiency of these massive megastructures? Or will the future of atomic engineering pivot entirely towards smaller, highly advanced modular reactors that abandon this massive physical scale altogether? It is a fascinating engineering frontier that is constantly evolving.